About anomaly detection. So till now, we have been dealing with regression and classification clustering. Mostly, we wanted to find out the structure and find the function between X and Y somehow through different methods and algorithms. There is a special case when the class of interest is minority, or if the data is not labeled. Still, in clustering, we want to detect a group of data points that may be of interest but get misdetected or misclustered somehow. So there are numerous, actually, very interesting applications. Normal data versus anomalous or outlier data. Very pertinent, very old statistics topic and machine learning topic. If we can define what is normal, then we can also label what is not normal. Definition is not straightforward mostly. The idea is that either the data points that are anomalous or outliers, they are generated by some different process or distribution and got included into this particular data set that we are looking at through some error, measurement, physical, or intentional error. If it's measurement error, we say it's noise, and somehow we try to tolerate it. But how do we differentiate noise from intentional perturbation in data by some actors who may be trying to mislead the process or the analysis? Similar to removal of noise, we want to detect and remove the outliers before going on to classification. Many interesting applications. In medicine, we want to detect the minority part of the DNA that is responsible for some terrible health outcomes, or in the images, we want to detect the tumor, which is always minority, has very little distinguishing features. Information security, financial transactions, numerous applications. Other than impacting our daily life, outliers also induce bias in machine learning algorithms. When we use parametric methods, the mean and variance usually that we use in Gaussian-based methods are terribly affected by the outliers. They cause distribution to go skewed, and it's better not to include them while calculating parameters. Different algorithms treat outliers differently. In case of decision trees, in the first assignment, we did pruning of the tree so that it doesn't learn outliers, just keep its focus on the normal cases. Don't get fixated on the outliers. KNN, the value of K is used to somehow get the best neighbors around the point that we are trying to classify. And the K actually helps somehow to alleviate the effect of outliers. In case of K-means clustering, you can imagine the estimation of cluster centroids will be disturbed if we have outliers in data. If we look at data set as one blob, we don't know there are subgroups in the data. One outlier can be easily found out, global outlier. However, if we have context to the data, some kind of group information, finding out which point is outlier for this group and this point is outlier for this group, it becomes like contextual outlier. This is an outlier in context of green class. This point is an outlier in the context of blue class. Global, we look at all data points without the information of groups within. Contextual, we have some context information. And collective is the third type. Here we are looking at a group of data points, tumor cells, that collectively are different from the whole data. And they can only be detected when we look at that group in collection. One by one, they may get assimilated to the normal data. A textbook example is of shell bidding, where one player creates multiple identities and try to influence the bidding price through fake bidding. Interestingly, our data set can have all three types of outliers. So we need to look at the detection of one type, second type, third type separately to come to some useful conclusion. So stepwise, heuristically, we want to define first what is normal to detect. That is usually done through parametric or non-parametric methods. Parametric methods need summary statistics. We need to train a model. And we use that trained model, or based on the summary statistics, the generative process, we use that to detect how far the anomalous data point is from the norm. And what we want to get out of such algorithm is the distance, measure how far a data point is from the normal. And we also want to label all the data points in terms of normal, abnormal. The difficulties we face here are how we can model normal and outlier. Usually we have only sample of the population, and not having access to the whole population restricts modeling the normal. For the contextual outliers, only machine learning won't help. We need to have some domain expertise. And also we need to have some idea of what kind of noise can seep into the measurement process so that we can distinguish between normal noise, let's say, and the anomalous data points. Depending on the type of the outliers, we have three different ways to detect them. Supervised models require labeled data for training. Semi-supervised, we only have labeled normal data from where we make the model of normal, and then any test data point, other data point in the training is we try to find the distance and decide. Unsupervised, usually no labels, and we still want to have some sense of what is what. We will look at some practical examples now in the context of unsupervised methods, and same methods we can then generalize easily into label data. So these are based on the availability of labels, different techniques or classification of the techniques for detecting outliers. Then based on the assumptions, if we assume the data is following some kind of Gaussian properties, or if it is not, we want to believe that the neighborhood is similar for any kind of data. The neighboring data points will be reflecting their neighbors. So anomalous data point will not be similar to the neighborhood of normal data points. And third is clustering-based methods, where we assume heuristic rule of thumb is that normal is always dense and large, and abnormal is always small and sparse. So if we can have a clustering technique, not like k-means, but some clustering technique that can have some kind of grouping mechanism in it to sort out the bulk of the data and the spread out here and there, salt and pepper kind of data points. And we can then assume that the sparse and small clusters are representing outliers. Some statistical methods to detect outliers. In statistics, either we believe things are normal, or if not normal, we want to use derive some parameters. We want to use non-parametric approaches that don't have any assumption about the parameters of the data. Before we move on, I want to refresh our memory about this normal distribution. We always start with normal cases. So in this distribution, the minority will live here in this tail, right-hand side, and left-hand side tails. And there are ways to measure the probability of a data point belonging to this distribution or family or population. If we know the true mean, then the probability of a data point belonging to this distribution is area under this curve, this yellow area. In statistics, we call the area under this curve. Let's say our data point is 146. 146 is around here. The probability that we come across 146 when we randomly sample this distribution, we call that probability p-value. P-value is area under the curve beyond 146. If that p-value is small enough, let's say 5%, then we can say it is less than 0.05. So beyond that point to the left-hand side, all the curve will be 95%. Beyond that point, 146 beyond all those points, the probability of coming across those points is 0.05, area under the curve. The p-value for 147 will be less than 0.05. 148 will be even smaller. 150 will be even smaller. So this is the global template for a Gaussian normal curve. Area under the curve for the minus infinity to plus infinity is 1. But it can help us decide whether a data point does it belong or not? If it belongs, how much? Based on the p-value. So can we use this basic know-how to analyze some data points? Let's see how. So a famous score that we just looked at, the original scores like 55, 70, 85, 100, 150, all the data points that we have sampled from this distribution, if we normalize them, every data point minus the mean of the points divided by the standard deviation, we get a score, z-score. Z-score standardizes the scale. On x-axis, we get values between -3 to 3, actually minus infinity to infinity, but -3 to 3 will represent 99.7% of the data. So z-score can help us decide whether a data point is outlier or not. But that will apply only to univariate outlier detection. For one variable at a time, we can look at it and decide based on the Grubbs test. Grubbs test is what? It uses two cousin concepts in statistics. Z-score is when we have textbook says more than 30 data points, we can use z-score. If we have less than 30 data points, then there is a cousin distribution, student's t distribution, which approximates to z as number of data points increases, but it's very useful distribution, practical distribution for smaller data sets. So using the t-score in this formula, we are using t-score. If z-score is greater than or equal to this Grubbs statistic coming out of the right-hand side of this inequality, then we say that the data point is outlier. I can pull a simple example to explain how we can look at this. So we have the famous iris dataset. Here we see the standard dataset having three classes, 0, 1, 2, three different types of flowers, and the attributes or the features of the dataset are on the x-axis: sepal length, width, petal length, and width. To make things interesting, I put outlier here, belonging to class 1, this orange line. In addition to the outliers in the standard dataset, whatever technique we use, we must find this data point to be an outlier. Now, looking at this parallel coordinates, we immediately see that in sepal length, this data point is an outlier. For sepal width, yes, it looks like outlier, quite distant from the bulk of the data. For petal width, not so much. So petal width ranges from 1 to 7 if we look at all the values without knowing the classes or groups within. Petal width, I don't know. Let's see. So looking at the data points in just 4 dimensions is okay, but if there are 40, it's impractical. And even if there are only 2 dimensions, we don't want to do this ourselves. So for one feature at a time, univariate data analysis, let's create these z-scores. So we just take the mean of all the data points and the standard deviation and create the z-score. Each data point minus the mean of the data divided by standard deviation. And looking at this box plot, the intuition should be clear. The original data box plots look like there are 4 outliers. But since the data is not standardized, not scaled, if we scale it in terms of z-score, now the outliers stand out compared to the same data points, go farther away from the bulk when we standardize it. So you can see here, standardization helps pushing the outliers away from the bulk. Would you agree? So one benefit of having z-score, but looking at the box plot, now the outlier that I included in the beginning, that is also prominently outlying here, at least for these 2 dimensions. The z-score for sepal length and z-score for sepal width is showing that this guy is standing out. And it's also giving some sense of abnormality for these 2 data points. At least they don't belong to the bulk. And this one, right? Even here, this is farther away. If we look at the normal parallel coordinate representation of original data, it was not this much away. So we are now convinced that z-score helps putting the distance between the bulk normal and the outlier. So now we are going to calculate Grubbs threshold, which is nothing but the equation that I just shared. Let's look at that. We are going to use the t statistic for alpha, as I mentioned when we were doing p-value explanation. Oh, it's right here. Alpha is a threshold that you decide arbitrarily. Beyond that point, let's say, beyond this point, if any data point z-score goes beyond that point, I will decide that it doesn't belong. So cutoff threshold. It can be 90%. It can be 95%. On the left-hand side of that cutoff point, the curve is 95%. We will say the chance of making a wrong decision based on this threshold is 5%. We say someone is outlier, but that data point is not an outlier. It will happen 5 times, 5%, 5 times in 100 samples. 100 times we sample from this distribution, only 5 times we will make this mistake. They call it type 1 error, false positive. We say it's outlier, but it's not. It happens only 5 times in 100 samples, random samples from the distribution. So that represents our alpha. Now, same alpha we are going to use with t statistic. arbitrary, 90%, 95, 99, you choose. So based on that, we calculate this value. So t value. Alpha I'm keeping here 95. We can make it 99. This will be a smaller value. Come out will be smaller value. N is the number of data points that we are using. N minus 2 is the degree of freedom that we need to provide to the PPF is the distribution table. It will look at the distribution for T distribution is very much similar to the Z distribution. Or the tails are thicker. Only tails are thicker depending on the number of data points. The more the data points, T distribution becomes Z distribution. So we calculate the Grubbs threshold for 95% confidence interval and 151 data points that we have here is 2.7. If Z score is greater than or equal to 2.7, it's an outlier. But we do this Grubbs test for each feature, absolute value, Z value. If it is greater than or equal to Grubbs threshold, we say this particular data point is an outlier and we want to visualize it. The red color represents normal and the green color represents outlier. It should be. Otherwise, I agree. But so this, if you remember, at the tail of this data frame, original data frame, I put this data point, this one at the bottom. This is 151st data point. So this is detected by the Grubbs test to be the outlier. This one. If we look at the original values, if we look at the Z scores, so pay attention to the y-axis. First graph is original values. Second one is the Z score for sepal length, sepal width. So we are seeing this data point and this one are detected to be outliers. For petal length, notice we couldn't identify in the parallel coordinates as well. So Grubbs test couldn't catch any. For petal width, no. Even the data point that we have intentionally put as outlier is considered to be normal when we look at univariate outlier detection. Here comes the need to look at the data in multivariate way. So univariate can detect outliers, but it has some limitations. Looking at the data point as a vector or combined features, we can still use Z-score, but we are going to combine. We're going to combine Z-scores for all feature by squaring them. So that minus plus don't cancel out, we square them, sum them, we get a value. If Z-scores are combined from multiple features after squaring them, their distribution follows chi-square distribution. And from the chi-square distribution, the logic stays the same. Just like here, for the normal distribution, we can put a threshold. Beyond that threshold, we come across a point. Beyond that threshold, we decide it's an outlier. Similarly, for the chi-square distribution, now combining the z's is not following the new number v, is not following the normal distribution. It's following chi-square distribution. If we can have some threshold for chi-square distribution, we can then identify a whole vector being the outlier. So let's aggregate. We aggregate these scores, sepal length, width, petal length, width, squared, summed, row-wise, and we create aggregated Z value. For this particular aggregated Z value, we are going to now want to have a look on the distribution that it will create for chi-square with 4 features. The degree of freedom for the distribution is 4 because we have 4 features. So on x-axis, I'm putting the all possible values that we are coming across for this particular combined value of z's. Minimum is 0, maximum is 35. So this is the shape that changes depending on the degree of freedom. If degree of freedom is 1, the shape will be different. But for 2, this is the distribution that we are going to use. So if the value lies here, if the combined value of z's that we just prepared, if it lies here, the probability that it belongs is almost 0, right? Actually, beyond 10, we can decide, because beyond 10, if we make a decision that some feature vector is an outlier, the chance of making that mistake of wrongly convicting or wrongly putting a feature vector as an outlier is very little, 0.01. 99% of the time, we will be good. Right? Just like normal distribution, the area under the curve is 1 here. So on the y-axis is the probability of coming across this value, 10, 0.01, 0.02. So how do we decide which point is needed? We say we want to be 95% sure, or 99% sure, or 99.9% sure. So we will arbitrarily give that decision threshold. Here we are using 95. And we will give how many degree of freedoms or number of features there are combined in the new value. So if more than 9.49, let's say, more than 9.49 is around here, then we can decide that particular feature vector doesn't belong. So we just compare this threshold with the aggregated z. If it is greater than threshold, we want to have a look on those data points and do this. This is aggregated z is scaled here because the values are going up to 35. So just make it look like a little visually better. I scaled them using min-max scaler, but z values here are the aggregated values. So we aggregate them, square each value, add them, and that added value, when we scale it with min-max, they all fall here, except the outlier that we put intentionally. So whole vector is detected here as an outlier. Visually, we can see that. How about the others? So if we run this, here we are doing what? Looking at z in the corresponding chi-square value, p-value of chi-square distribution, and using that, we see there are 1, 2, 3, 4, 5, 6 data points detected being outliers, whole features in the whole data set. This one we put intentionally, but other than these are the data points. So the p-value, based on p-values, the probability of making the wrong mistake, we said 95%, we want to be sure. If we plot the p-value for the corresponding this data point, it is almost 0. The p-value for this data point is almost 0, almost 0, 0, 0. Others are having good confidence. They belong to the normal, but they are edge points. These are the edge points. So are you convinced enough?
Yeah.
The second plot is showing the p-value, the probability.
Right. Yeah, I guess I was looking at the scale that has the standardized.
One means this does, it's 100%. If right. we, for this point, if we sample the distribution 100 times, we will find this point coming out of the distribution. But as we go below, these points the p-value will be less and less. And for the outliers, the green points, we are so less sure. Less than 5% we will come across this kind of points. If we randomly sample the distribution who generated this data 100 times, only 5 times we will find these points.
Okay. So my question was, like, if you look at the middle plot, right? There's if you look on kind of like the left-hand side here, right, the second green point from the left. Yeah. Right. There's another point that's like right next to it, right?
Exactly.
That one. So we're like, what? Maybe very slightly more confident on that one. So it just makes the cut of being like not an outlier, but
right. I agree. So these two feature vectors, let's say, they are very similar, but one is closer to the normal and one is going beyond the threshold of 99. If we relax the threshold, let's relax it. We say we want to be 90% sure. Now the value came down, so we will see that point becomes the outlier. This is the point we were talking about, right? Mm-hmm. So now more outliers, and now we have another contention here. So these two are in the neighborhood. And there is always going to be a border. So one family lives in this country, the other family lives in that country. This is the property of binary threshold. So we can have another AI technique to give like soft assignment, like fuzzy membership. So this point is for sure 100% outlier, but this point is 50% outlier, 50%. I don't know, not a solution. But yes, when we say 90%, we want to be 90% sure. Then 89.99999 will become normal. So we have to live with that. Let's say 99. We want to be 99% sure that we don't make a mistake. Now, this time, only the point that we added as intentional outlier, only that point is going to be, only that point is the outlier. When the third plot is showing the log scale, on log scale, we can see, so these values, second plot values are logged. So in that case, we see the distance is quite pronounced. So this is for sure outlier. And we see that in univariate analysis, some data points we can miss. So combined in multivariate analysis, we square the z-values, add them up. The resulting value is coming out of chi-square distribution. Chi-square distribution, since we know how many values are combined, if we know that is m, the degree of freedom, and from there we can identify the whole feature vector being the outlier. The third idea is, now, up till now, the Gaussian things that we had, the Gaussian is circular. So we are not taking care of the ellipsoidal shapes of two variables. If they're ellipsoidal or shaped in a particular way, then if you remember, we were using covariance matrix to model that non-circular but correlated shapes. So we have another extension of normal distribution. If we vectorize our formula for normal distribution, it looks like this. This guy that we exponentiate to, the square root of this guy is called Mahalanobis distance. Mahalanobis distance is considered to be better than Euclidean distance or circular kind of distance. It's not sensitive to the shapes. It is sensitive to the shape of correlation or covariance. It responds to it better. So we can try looking at Mahalanobis distance. So here we have each data point distanced from the mean of the whole data points, whole data set. And when we take this, we will have, we take covariance, inverse it, and create the mean from the iris data. And in this for loop, we are going to the every row of iris data and take the difference from the mean vector, transpose it and multiply with the take dot product with the inverse of the covariance, and then take the dot product with the same iris row minus iris mean. Same formula we see here. Since we start with a different shape, our data is tabular, it's like number of rows first and columns. So we put t here in the code instead of here. If we transpose the data first, then we will look at the similar formula. Anyways, so this distance is from a given point to the mean of the data. And if we calculate that, based on these distances, we again use the same chi-square threshold. And here, when we plot it, Mahalanobis for the same threshold is telling that only the data point we intentionally put as outlier is the outlier. Rest are normal. Other than this, we have been doing GMM. If you remember, GMM also models. We, in expectation step, we do some estimate of the parameters, and then we say, okay, maximize the likelihood of data points coming from the distribution that is following these estimates, and repeat that process again and again. That can be used to detect outliers as well. So if we, because we have soft assignment there, and there will be some data points that belong to nobody or for no major cluster. So we can, based on the probabilities of assignment, we can say, okay, these vectors don't look like coming from normal data. All the things that we have gone through till now are parametric, and they have the same drawbacks that parametric methods have. We assume the data is normal, only then they work. In case of violation of that assumptions, we can use non-parametric methods, and they are more general. Even if things are normal, we can still apply them. They start by kind of binning the data. So binning is always risky. With what size? So shape of the distribution that we estimate, it depends on the bin. Other than that, they are quite generalizable methods. So we estimate the density of the distribution, and based on that density, calculate parameters, and those parameters lead us to the outliers. Other than histogram, we can also do computationally intensive technique of depth-based anomaly detection, where we construct convex hulls of data points. So outer circle, next outer circle till the center of the data points. So now we are not assuming they are coming from normal distribution. We are just looking at the circles or hulls. And now we can decide. So for sure, depth 4 is the center. Depth 3 is next to the center. Depth 2 is cannot be outlier, but in depth one, we can now decide which one is outlier. Visually appealing, but quite expensive method in case we have 200 or 2000 dimensions. Finding out the convex hulls is computationally intensive. So far, so good. So this is how we go about anomaly detection. And the methods that we have learned so far, in one of the prominent ones was support vector machines. Support vector machines are also very successful algorithm to detect anomalies. In that case, we train a machine to detect one class of interest.